Okay, so good afternoon to everybody. My name is Francesco Cottone. I'm a researcher at University of Perugia in Italy. I'm from NIPS laboratory at the Department of Physics and Geology. Today I'm going to talk to you about the vibration databases and simulations tools that are provided within the Enables project. Okay. So the main objective of this webinar is to show to everybody that is interested in using virtual access resources of the Enables project, the use of the content and the use of the vibrational energy harvesting databases, and the use of new simulation tools that are just provided just now. They are online. The last version is already online, and I will show you how to use it, how to access it. So at first I will give just a brief introduction to the Enables project, and then I will pass to the vibration database and the simulation tools. So to all researchers that are interested in energy harvesting for powering the Internet of Things, the Enables project is a great opportunity provided by a European funding, that is H2020, because this project is a European infrastructure for powering the Internet of Things. In particular, this project collect all the know-how of the researchers around Europe and the facilities about the technology for powering Internet of Things that are available in Europe. We are 11 partners on this project, and the project provides free of charge access to the every kind of feasibility studies and to access to the libraries, so also online resources, and to access to all the facilities like laboratories, equipment, tools, and so on. For researchers that want to start new feasibility study or new projects on energy harvesting or on power management and energy storage, all the technologies that can enable the Internet of Things. So we know everybody that today wireless sensor networks are possible only if we solve the problem of the powering. In particular, if we solve the problem to make this technology self-powering, so without the possibility to go on without maintenance, and just giving the possibility to leave all these sensors around in the ambient and leave them there, and just we can access to this sensor without changing batteries and so on. Okay, so the main objectives of this community is to get together all the know-how and experience and expertise of the people that who are working on this research topic. And this research field includes energy harvesting, energy storage, micro power management, and system integration. So all the facilities and institutions that are part of this community offer the access to their lab for a few days, for a few or more days, to the researchers that are interested in doing some early stage experimentation or design of their technology. So the objective is to create powering the Internet of Things community to enable the development of wireless Internet of Things devices, so miniaturizing also the devices and make sensors autonomous, and integrate energy harvesting, energy storage, and power management solutions. So this is the main objective of Enables. So we are really happy to welcome people that are interested in joining this community. It is for free, and the people can access both to the laboratories, equipment, or also to the knowledge of people that are part of this community. and also to online resources. In particular, the virtual resources that are available now, they are from University of Perugia and from University of Southampton. In particular, University of Perugia is focused on providing a vibrational database that collect all kind of vibrating signals from any source. And the user that register can access to this vibration database and download each kind of signals and can make virtual experiment on this type of source on vibration energy harvesting. But they can make also real experiment in the lab by just reproducing the vibration with a shaker. So just downloading the signals and put as input this signal to their setup and make a real experiment in laboratory. The users are required to register from the Enables website, and once they are registered, they can have access to the facility, to the online resources. And they can go to the vibration data, as you can see here, click on it, and then click on the application form. Once they get into the Enables inquiry form, they just fill the form, and then they have free complete access. And then in the energy harvesting databases, users can choose energy harvesting data repository from University of Southampton or real vibration database that is provided by our university. And also now there is available an early version of some web simulation tools, and so the user can have access to these tools. Okay, now and then I will show you more in details the usage and the content of these instruments. Okay, so basically, okay, now we see here in this slide the web page of real vibrations that were developed previously by NIPS laboratory and then now updated under the project of Enables. And in this page of real vibration, the user can access to the right here, can make a login, and once the user is logged, he can download any kind of signals. And so the signals are under different categories. So it is possible to make a search by category, like cars, trains, airplanes, and so on, human beings.
Don't have enough sugar for them.
And then, okay, once that...
Look like a plate of pasta. You prefer to be something sweet?
Sorry, I hear some microphone open. So in the signal web page, the users can search a particular signal or directly in the search box or by category. And then in this page, you can see all the type of signals that are recorded, the power spectrum, just a brief, the length, the time length of the signal, and the sampling rate and the acquisition kit, which has been used to record, to make the acquisition. Okay. And also there is a new box that is called categories. So you can also click on a specific category and have a list of all the signals under that category. So as you can see, we have from human motion, domestic devices, transportations, bridges, so infrastructures like road or bridges, and bike, public places, or music, or animals. So, and I want to stress the fact that this database is not static, so it's dynamic. Everybody can contribute to it by just contacting us, just asking by email to the contacts, to the administrator of this database. They can upload their signal. So it is important also to respect some specifications on the acquisition characteristics the kit, for example, so the sampling rate, the length, and so on, to upload their signal. But everybody can participate to this project. This is very useful and for researchers, because if a particular researcher needs to test a particular, to check a particular signals, or for example, or just need to download a particular signals to test the application that he is targeting. For example, if he's developing a vibration energy harvester to get energy from a bridge, or from a particular, or from a vibration of the wings of a plane, or whatever, if he has this particular data, he can upload the data, so enriching the database, or he can and then use the simulation tools to make a fast simulation in order to estimate the average power and the energy. Here you can see some example. In this example, if you click on a specific signal, there is a new web page that is opens and summarizes all the data set information that appears. In this case, for example, we have taken some vibration from a cat that is walking, a working cat. So we attach the data logger on the collar of the cat, and then we recorded all the movement and the acceleration in the XYZ direction of this animal. And so you have the time series and the power spectrum. Okay, this is just an example. In the file, in the dataset file, you have the 3-axis acceleration, as I said, and you can see directly the power spectral density in our website, but you can also calculate by performing an FFT. You can see the time length, and you can perform, and you have also some additional data such as root mean square and the standard deviation of the vibration, as you can see here. So you have the length, the sampling rate, the acquisition kit. Also, the acquisition kit can be updated, so you can upload the specific characteristic or model of your acquisition kit. So if you are using National Instruments device or whatever, you can just upload all the specs inside our database, and you can just perform any kind of virtual experiment on these files. And you can share, of course, you share your file to every researcher that is interested in using this database. As you can see here, there is a child swing, for example, and most of the signals that are in the database, you can notice that they present the most of the energy at low frequencies. This is normal because normal vibration sources in the ambient typically below 100 or few hundred hertz of vibration spectrum. So the main peaks of the main energy is distributed below few hundred hertz in the power spectrum. So this is very important because for researchers, because a researcher can understand suddenly that we have to, in order to get energy from vibrations, we have to design a low frequency, specifically low frequency vibration energy harvester, so optimized for low frequency, and the user can make experimental tests on these particular signals. Here there is also the data kits page, and in the DAQ kits, the data acquisition kits page, you can see a list of the data acquisition kits that have been used to record most of the signals that are already present in the vibration database. And also, of course, the specifications. As I said, we very welcome users who want to actively collaborate and participate to this project, and in updating the database and the kit list also. Okay, and now we pass to the simulation tools for vibration energy harvesting. At the moment, we have just two modules, two web applications that are available in the Real Vibration website. One is the vibration energy harvester. It's called vibration energy harvester. It's actually a very simple and theoretical. It's a simulator based on a very simple theoretical model. It is a very well-known model in the community of vibration energy harvesting from William and Yates. Here you can also find the reference to the work, scientific paper of the William and Yates about this model. Typically, at the very first step, when you design a vibration energy harvester, you have to imagine that a vibrational energy harvester is based on a system that is an oscillator composed by spring and dampers. And this oscillator can be directly forced, or it can be forced by inertia. If we consider an inertial mass, like in this image, an inertial mass that is attached by a spring to a box, and this mass is damped by two damping factors. One is mechanical and the other one is electrical one. So the transduction from vibration to electricity is performed by the electrical damper. So in this very simple model, you can pass as input these parameters: the inertial mass in kilogram, the stiffness or the equivalent stiffness of the spring, and then the normalized mechanical damping and electrical damping, and then the max acceleration. In this model, we consider that we are just exciting this box, this vibration energy harvester that is independent from the type of transduction. We are exciting it by an harmonic excitation, and so a simple harmonic excitation that span over all the frequencies that goes from 0 to at least the double of the resonance of the system. So I will show you now how it works. Let me just share my screen. Okay. Okay, let's go to the. Okay, let me share my screen. You can see my screen. Sorry, you can see my screen now.
Yes, we can. Yeah.
Okay, so I will go to the first. If you see, I'm clicking on the real vibration simulator. As you can see here, you have this page, and this page you can also try at home going in this link, but you have to make a registration first. If you can see here, I can change the mass, like 0.1 kilogram, 0.2. I can change stiffness, Newton over meter, and then I can change the electrical damping or mechanical damping. As you can see, by just changing or clicking the parameters, the curves dynamically changes. And so it provides you an insight, an early estimation, or how the system the system behaves under harmonic excitation. Here the peak of the power correspond to the resonance of the system, that is around, in this case, around 11 Hertz. But if you change the mass, of course, this affect the resonance, as you can see here. Now the resonance is, if I put just 1, for example, now the resonance is 5 Hertz, okay? And I can change the stiffness, so we can change stiffness like that. As you can see now, with the stiffness, with a very more soft stiffness, we get 0.5 resonant frequency. So we can play with the mechanical, electrical, and mechanical damping. The mechanical damping, you can, of course, you can estimate the mechanical damping of your device by just measuring the quality factor, for example. As you know, the mechanical damping is the inverse of the quality factor. The mechanical damping divided by 2. So you can perform this, and you can make an early estimation. Also the simulator provides you suddenly the value of the max electrical power at peak resonance in milliwatt, and the natural frequency that is here 0.5 in this case. Okay, so before developing or making a design of a very complex vibration energy harvester, the researchers should perform this calculation first. And this is very useful because they can have an idea on how much maximum power they can get for an ideal system. Okay, now I pass over to the presentation. Sorry, let me see if you. Okay, I have to go to the previous slide. Okay. Okay, here we are. Okay, you see your the presentation? Sorry. Okay.
Yeah, we're fine, Francesco. Yeah.
Okay, sorry. So going on, this is the theoretical model that is explained, the theoretical model used for this simulator. As you can see, it starts from the governing equation, the dynamical equation, and the mechanical damping factors. And then the excitation, this harmonic excitation in this case, going from 0 to the double of the resonance frequency. So in the simulator provides the power response over the frequency, and the power response over the frequency is given by this formula, basically. So the maximum power is obtained by just equating the resonance to the input frequency, and then the maximum power that can be obtained by varying the parameter of the electrical and mechanical damping is obtained when the electrical damping is exactly equal to mechanical damping. We know very well that this is in practical this is not true, at least. It is true for an ideal vibration energy harvester, but when you design a real vibration energy harvester, you have to take into account of various aspects, like the maximum displacement of the mass, like the real damping that cannot be varied as you want, and also the electrical damping that is constrained by the type of transduction, if it is piezoelectric or inductive or capacitive. Okay, now we pass to the second simulation tool. The second simulation tool that is now available, you can also try by going directly to the website once you are registered. The second one is exactly now is not anymore independent from the transduction, but is specific for piezoelectric generators. In particular, the simulator perform a calculation of the numerical equations of the dynamical equation of the system of a piezoelectric beam of cantilever. The beam of cantilever is model is based on theoretical model from Roundy and Bright, and also from other paper like the one that I've done in 2015 and so on. And this is based on theoretical model, of course, so it doesn't account for all the aspects of a real piezoelectric generators, but it can provide you quite a good estimation of the behavior. In this simulator, I show you the theoretical model. The theoretical model is based on two coupled equations. The first one is the Newton's equation, in which the oscillator is excited by an external acceleration of the box that is on the right-hand side of the equation. And the second equation is based on the Kirchhoff law, because in this case we take into account of the resistive load that is connected to the mechanical system. So the resistive load affects with its impedance affect the mechanical behavior of the system. So it's a system of two coupled equations, and not anymore just one formula like previously in the first simulator. In these equations, all the main parameters that you can see here, like the stiffness, equivalent stiffness of the spring, the electromechanical transduction coefficient KV, and the other voltage over speed over velocity coefficient KC, the resistive load RL, and the effective capacitance of the piezoelectric layer is all described here and represented in this two-couplet equation, and they can be changed by changing the input parameters of the specific like geometry or material properties of the system. And from that, all these parameters are dependent parameters derived by the input parameter provided to the simulator. So all are calculated as you can see here. So they take into account of the Young modulus, of the elastic modulus of the piezo layer and structural layer. They also depend on the geometry, as I said, and the inertial mass. Inertial mass that is attached on the tip, and also on the inertial moment of the beam. So they are automatically calculated from the input parameters. I will show you now. I will pass again to the website to show you some example of the usage. Okay, now if you go to the get back. If you go to simulators, under simulators you find piezoelectric energy harvester. There is now you can see you see 2 pages, but 2 buttons, but actually you should see, if you are not logged in, you should see just one. This is called piezoelectric energy harvester. Inside here you see the main model that is sketched here and at the top, and then you can change the time steps for that is the number of time steps for the numerical integration of the governing equations. You can choose the database signal, or for the moment just a sinusoidal input. If you choose a database signal, then you can choose the specific signal from the database, like for example elevator, air conditioner, train, and so on. If you choose train, for example, sorry, maybe you don't see very well. I cannot, okay, sorry, I cannot zoom my page. Okay, if I make push run, what the simulator does, it load it load the acceleration file over the time, and provides you as output the displacement of the inertial mass and the output voltage. Okay, if you then okay, you can change the number of time steps in the calculation. I show you another example. If I pass a sinusoidal signal, for example, I'm giving an input frequency of 30 Hertz, and as you can see in the first plot, you see the black one is the acceleration series over time. Then in the second, you see the displacement of the inertial mass, and the red one provides you the output voltage across the resistive load. You can also change the resistive load, as I said. If I put, like, for example, 10,000 ohm, and then you can also save the data once you have performed the simulation. Now, if I change, for example, let's put a realistic load resistance. You can see here, this is the voltage. This is going from minus 2.5 up to 2.5 volts. Of course, you can change the input frequency and run again and get another response. Once you are okay with what you want to get, you can save the data. You can push to the button save data, and you give a name to your file. It's a normal text file with column with 3 columns. The first one is the time, the second and the third are the displacement and the output voltage. the columns are separated by tabulation. So you have the file. Okay? As you can see here. So, and you can change the beam length, the beam width, the tip mass, if you want to add a tip mass. You can change the piezoelectric layer thickness, the structural layer thickness, and the mechanical damping ratio that depends on the measure. You can measure it if you have a real device, or you can just imagine how much can be the quality, mechanical quality factor of the system, and you provide and you calculate the mechanical damping ratio. So this is an early, I want to stress the fact that this is an early version of this simulator. I will update it with more features, like, for example, the possibility to provide a random noise or exponentially correlated noise or other type of input signals. And also, we are harmonizing all the files of the database, because some files are sampled with a certain sampling frequency. Some other, for example, some of the files are at 100 Hz, that is very low sampling frequency. Some others are 3000 Hz and so on. So we are updating it, and it will be, but this early version is already working. Okay, going back to the presentation, I'm almost done. I'm sorry for Alex if I'm taking too much time. In this, okay, so in this simulator, by default, we provided some parameters that are similar to that of the commercial piezoelectric device that is from Mide Vulture. Maybe you know this company. This is a piezoelectric generator that can be purchased online, and it uses the PZT5H material, which has a strain coefficient around -190 10 to -12 meter/volt, and a relative permittivity of 1,800. But of course, I will also provide the possibility to the user to provide a specific piezoelectric strain coefficient for the development of their specific device. Okay, so I'm concluding, and then I will pass the word to Alex for the repository from Southampton. In conclusion, I want to say that Enables provides free of charge. Sorry, maybe you see. Sorry, I just want to share the presentation now. Okay, just to conclude. Okay, so in conclusion, what I want to say is that Enables provide free of charge virtual access resources to researchers that are working on vibrational energy harvesting for powering Internet of Things. And the online resources from University of Perugia and Southampton are about databases on all the natural energy sources or artificial energy sources that are available on the ambient, and the simulation toolset that is under development. It will be more rich in the near future, but at the moment it can provide some useful tools to the researchers. So the researchers, in conclusion, have the possibility to perform this kind of virtual experiments on the vibrating signals that are present on the database, and so to make an optimization of their harvester design without spending money on making trials and errors with the new prototypes before optimizing all the parameters of the design and testing this design virtually. Okay, so I concluded. So thanks for your attention, and these are the people working on this project at UniPG for the Enables. Thank you very much.
Okay, so I'll just take over. Can everyone hear me?
We can, Alex. Yeah, we can hear you.
Okay, so Francesco, I think you need to stop sharing so that I can start.
Okay. I don't know if for the question I will wait at the end. Okay.
We'll wait at the end. We'll take all the questions at the end.
Okay. Okay. Sorry.
Yeah. Thanks.
So yeah, my part should only take a few minutes to go through. Okay, can you see my screen, see my presentation?
Yeah, you're fine. Yeah.
Yes.
Great, okay. So the University of Southampton's data repository began as part of the Energy Harvesting Network, which was a physical engineering and physical council, Engineering and Physical Sciences Research Council funded project to bring together researchers in energy harvesting, primarily in the UK. So we have used the contents of that database and brought it forwards as part of the Enables project. The main motivation for this database was to provide access to long-term vibration data, so that you can get a real idea of how an energy harvester is likely to perform in a real application, which you may not get from a snapshot of a few seconds. So in common with the database from Perugia, our database includes samples from cars and vans, bridges, domestic appliances like washing machines, tumble dryers and fridges, some human-based data, and also some industrial machinery, such as a Ward London-Stat motor and a hot water circulation pump. So I think the basic motivation is very similar to Perugia's. So we want to make data available so that researchers can use it as part of their development of energy harvesting systems. We also invite contributions from the community, although most of the data on the database is from University of Southampton and University of Bristol. So there's a real need for long-term data. So a few years ago, you may just have found tables in a paper. So the table on the right-hand side shows you a publication from 2003, which was supposed to show the amount of vibration in different applications. So as you can see on the table here, we have the car engine compartments with a supposed amplitude of 12 meters per second squared and a peak frequency of 200 hertz. But ultimately, if you're designing an energy harvesting system, you don't want to rely on data that you may find in a table that may just give you an idea of what it's like in a few seconds on a particular piece of machinery. You want to understand the dynamics of that vibration, perhaps what contributes to it and how it behaves over time. So you want to be able to design effective energy harvesting systems using as much data as possible. So we've collected long-term vibration data in a range of applications. As you can see, some of our data collection exercises here. You can see in the center of the slide, we have our accelerometer mounted onto a district hot water circulation pump. So this pump actually circulates hot water around the whole main campus of the University of Southampton. And the data shown on the left-hand side here is from that pump. So you can see there's a mixture of vibration signals within that trace. The dominant vibration in most cases is from the rotation of that motor, and it changes its operating speed based on the demand for hot water from various parts of the campus. So this is an example of where use of a single parameter can land you in hot water. So if you designed your harvester just for a single amplitude, a single frequency, the likelihood is that you'd be harvesting nothing for most of the time. Similarly, on a vehicle, and I'll say a bit more about the collection of data from vehicles in a moment, we've looked at long-term data for a typical commute. So I drive quite a long distance, or I used to before lockdown, on the way to work and back, and I've attached an accelerometer to various parts of my car during that commute. So you can get an idea of the dynamics of those vibrations in realistic conditions. So this is one of the test setups we use. So we bolted an accelerometer to the top of the engine. And on the right-hand side, you can see the trace of vibration on the engine. So this is a 45-minute drive in a mix of road conditions. A unique feature of the data that we've collected, though, is that we've simultaneously collected data on engine parameters during that drive. So at the same time as we were collecting vibration data from the engine, we were also logging the engine parameters, things like the engine load, the RPM values, so that we could then go and look back at the data and see what contributes to vibration and in what conditions vibration is most significant. So by doing that, we found that the dominant vibration frequency in this application was at 2 times the RPM of the engine. So this was a 4-cylinder petrol engine, so you got 2 firings per revolution, so that explains why you got vibration at 2 times the RPM of the engine. We also found the vibration amplitude was very highly dependent on the loading. So when you put your foot down, you'll find that the vibration on the engine increases significantly. So we've captured vibration in 3 axes at high resolution, so I think these were sampled at 1024 Hertz. So it enables you to look at the profile of vibration to help you to design your harvester. Similar to Perugia, the data is available both as raw data to download and also as processed data. So you can see we've got the waterfall plot here and also the individual plots of X, Y, and Z axes for the test. And also for some of our tests, we've generated videos, so you can play the vibration characteristics of each of those tests on YouTube, so that you can visualize the FT going through time. Looking at the detail of what's been captured for the car journeys, we've collected the data on the engine parameters that are high frequency as well. I believe it was logged once per second. You can see this journey has a range of speeds up to motorway speeds, and then getting into the urban environment as we get into Southampton. Zooming in, so we've got a snapshot once per second during the drive, and then if you click on one of these arrows, you can open this up in Google Maps or Google Earth, and you can visualize, you can see the actual parameters of the engine at that point in time. So as I mentioned, we've got the engine load, we've got the engine RPM here. So these are probably the most important parameters for looking at contributors to vibration from the engine. What can we use that for? So we can use it to help us with design decisions, to help us to decide what type of harvester would be most appropriate. On the right hand side, we have a characteristic from a vibrational energy harvester that was produced at Southampton a few years ago. So it exhibits soft non-linearity, and you can see that on the blue line, when the vibration input is sweeping upwards in frequency, we get a very low power output from the harvester until about 47.5 Hertz. And then we sort of jump up to giving a decent level of power output. Going the other way, though, if we're going downwards in vibration frequency, you can see you actually get some advantages by operating at a slightly lower frequency than 47.5. However, there's a cliff edge in both directions, right? There's a cliff edge on the way up, which means that it's hard for you to get up to a significant level of vibration. And also there's a cliff edge on the way down. So if your vibration of your engine or whatever piece of machinery you're working with drops below a certain frequency, then you effectively get almost zero power output. So just looking at the behavior of the vibration sources can give you a lot of useful information to decide on the appropriate type of energy harvester. It also allows evaluation of performance of harvesters in simulation and in the lab. So Francesco has spoken in detail about how you can use this data for simulation purposes. We can also play back vibration spectra through our shaker, so we can replay the vibration that we've captured from the real world through our shakers so that we can do a realistic test in the lab, which gives us a good idea of how that harvester is going to perform in the real world. So we're not just looking at peak frequencies and amplitudes, we're replicating the spectra of the vibration signal. So that brings me to the end of the Southampton part of the presentation. So the data for this is available from Southampton and from Perugia through the Enables website. You just need to sign up. It's a very quick process. You can import that into simulation tools. You can use it with a NIPS tool. Alternatively, you can use it to replay through a shaker in your lab. So this real data permits real applications to be considered when you are designing energy harvesting systems. So that brings me to the end of my part of the presentation. Thank you.
Yeah, thanks, Alex. Thanks, Francesco. I think that was very interesting introduction to the data and the simulation tools available in the Enables Virtual Access. So what I would like to know is to invite the audience to, if you have any questions for Alex or for Francesco, please turn on your microphone and you can ask directly, or if you want to send it using the chat, whatever you prefer.
Hello.
Good afternoon.
Good afternoon. Thank you very much for the nice talks. I have one simple question. My question is there a application scenario or condition where the vibrational amplitude is about several millimeters and the frequency is about dozens of hertz? For example, the vibrational amplitude is about 2 millimeter and the frequency is about 80 hertz, but the corresponding acceleration can be very high. It's about 50 G. Is this kind of a vibration condition how do you say that, available in the environment? Thank you.
Okay. Nicholas, you have muted your...
Yeah, no, I was going to say, that's either one of you want to take that question, sorry.
Okay, I don't know if Alex wants to reply or...
So I think in the real world, if things are vibrating as a low frequency, it's quite common to see significant amplitudes of vibration. A lot of our testing has been on things like engines and motors. So I think I can just understand why you're asking this question. Are you worried that vibration amplitudes are going to be too much for a certain type of harvester? Or are you particularly interested in maximizing the amplitude of vibration?
Based on my design, I find something interesting at a very larger vibrational amplitude at even high frequencies, but the corresponding acceleration is very high, about 50 G. So I'm not sure if this kind of a performance can be used in real world for real application. So that's why I ask this question.
Okay. So at Southampton, we've developed harvesters that mount onto engines. So we developed a harvester to go onto an engine on a ferry that goes between Southampton and an island about a couple of miles off the coast. It's a macro scale generator though. It's pretty large and it gives good levels of power output, a few milliwatts typically. But obviously, yeah, you need to be careful when you're developing a harvester to ensure that large levels of vibration are not going to cause damage. So there is also always a risk, and you need to account for that risk in your design. So ensure that you don't experience physical damage to the harvester when amplitude exceeds the amplitude you expect.
Okay, I see. Thanks. Thank you.
Thanks, Alex. Any other questions from anybody in the audience?
Nicholas, it's Mike here. It's my case here. I'm the coordinator of the Enables project. So thanks, guys. Very nice presentation. I guess one of the visions we have for Enables is to create, repositories of ambient energies and for various people to develop parts and systems which are standardized and interoperable. So if you go onto the Enables website, not only will you find the repositories of data, if anybody is characterizing any parts, we've also come up with standard methodologies for characterizing parts, because what we would like is for people to share their parts, whether they've done a characterization of an ambient energy, or whether they're developing transducers or storage devices, and to encourage people to come together and put their various devices into systems which will work in real life ambient energy. So please go and explore our website and have a look at this. I'd also like to take this opportunity to say that in addition to the virtual access of database, we have the transnational access program that you heard at the start of this call. And if anybody would like some assessment of ambient energies to be done, that's a possibility for us to do under the Enables program, giving access to our laboratories to do some characterization. And of course, the idea then is that that data will be shared with the Power IoT community.
Thanks, Mike. We had also received a couple of questions in advance. I think mostly they were referring about simulations for wideband for Francesco. So did you have the questions yourself there, Francesco?
Okay, I have a question by email. Yes, is how to test a design for real-world wideband excitations. Is that the question?
Yeah.
Okay. So you can, if you have a design, you want to test it under wideband excitation. For example, you can test virtually, as I said, by just using the simulation tool in our database. If you have a particular wideband excitation, like a random noise or exponentially correlated noise, or a noise from a device or whatever, from whatever source, for example, a bridge or a machinery, or most of the vibrating sources from the ambient are wideband. So most of the sources that you can find in the database are actually wideband vibrational source. So you can test both virtually by just passing as an input to your vibration energy harvester, or you can test, as Alex was saying, you can test by just downloading the signals and passing the signal to a shaker. If you have a disposal, a shaker in the lab, you reproduce or you play the same wideband excitation. You attach your device on the shaker and you test the shaker. I don't know if I replied, if I understood well. What I'm saying is that you can both test your design first by simulation, and then secondly by laboratory setup with the shaker.
Good. Thanks, Francesco. Are there any other questions for any of the speakers? Okay, what I would suggest, if you have any other questions that you think about later on, please contact me by email, and then I can pass it to Francesco and Alex, and they can reply to you by email. So I would like to again finish by thanking again Francesco and Alex for a very interesting presentation. And remind you again, all this data and all these tools are available. All you have to do is to register and to become a user. It's a very simple process, takes only a few minutes. So if you are interested, you think you can benefit from this data or from these tools, please contact us and we get on.